Good afternoon, all. In our laboratory part, we have already completed our 10 experiment in your batch, right? So today we are not going to start with lab session because we already have completed their all laboratory experiments. So today I'm going to start with our regular class session, right? So in our lecture session, we have completed the up to unit 2. That is, we have discussed about various number system and all combinational logic circuits, right? That is in the chapter number 1 and 2. We have already completed that part. Now, according to your syllabus, unit number 3 we are going to start today, and that is belongs to sequential logic circuit. So let me just share my PPT and then we'll discuss that today here. Okay, I hope my screen is visible to everyone, right? Is everyone able to see the screen? The slide which I'm showing you right now? Okay, that's fine.
Yes, sir.
Okay, so in the unit number 3, we are going to start with the sequential logic circuit. Before that, let me just give you the recap of the thing we discussed in our last session. In your lecture schedule, I'm talking. In last lecture, we were discussing about serial binary adder. We also have discussed about look ahead carry adder, and we also have seen that how to implement a parity bit generator, right? That is for error detecting code. We have to implement a parity bit generator so that based on the numbers we can add parity bit into it, right? So that part we have discussed in the last session of the chapter number 2. Now today we are going to start our session number 29 as per lecture session schedule, and in this we are going to start with unit number 3. Okay, so that unit number 3 belongs to sequential logic and circuits. So before we start this session, let us talk about what are the learning outcomes of our today's session. So today we are going to first introduce sequential logic circuit. Then after we'll be comparing between sequential logic circuit and the combinational logic circuit. That combinational logic circuit we already have completed in the chapter number 2. So we'll compare between that two circuit here first, and then we'll start discussing sequential logic circuit. And after comparison, we'll start illustrating the operation of the smallest unit of sequential logic circuit. That is what we can say a SR latch and the flip-flops. So these are the points of discussion of our today's session, and that will be your learning outcomes. So let us we start our session with the flip-flops and latch and the comparison. So first of all, understand what is the sequential switching circuit or sequential logic circuit or digital sequential logic circuit, whatever you say. So first of all, you can see the sequential switching circuit, or you may call it as a sequential logic circuit, that are the circuits whose output levels at any instant of time are dependent on the levels present at the input side at that time and on the state of the circuit, i.e. on the prior input level condition. What do you mean by this? For example, let me just tell you about that. Let us say this is the combinational circuit you have, right? In combinational circuit, what we are having some number of inputs, right? Like for example, if you have been given a function f of a b c d is equal to sum of the minterms, right? So let us suppose I give you that function written over here. Okay, suppose this combinational circuit is having the function implemented like this: f of a b c d is equal to some number of minterms present, right? Let us say 0, 1, 2, 5, 6, and 14. Suppose this is the function given to you, right? That's what we have learned in our previous chapter. That a combinational circuit is what? It is going to be implemented by the combination of various logical gates, right? So this logical circuit is going to be implemented with the help of that number of logic gates as per the function given here, for example. So what that will do, it will check the inputs, and according to the logic function you have implemented in your combinational circuit, you will be getting the output, right? So here, this is what the combinational circuit is, and that we already discussed. That in combinational logic circuit, the output which is present over here at the output side, if you are measuring at the time, suppose time t equal to t1, okay? So at this time t equal to t1, if you are checking about your output, then that output is only depending on what inputs coming at that time. Understand this thing, everyone. Sequential logic circuit we are talking about later on, but first of all you get a brief about your combinational circuit. So right now you can see the block of a combinational logic circuit. In that combinational logic circuit block, we have some function given. That is what we can say a Boolean expression. And that Boolean expression is going to be implemented with the help of various combination of logical gates. So when you put that same arrangement of combination of logical gates, based on the inputs coming on the input side, your outputs will be decided, right? But in that combinational logic circuit, if you are measuring your output at some predefined time, let us say t equal to t1, then that output coming from that combinational logic circuit at time t equal to t1 will only depends on the input coming at that time. So you just refer this term. So whatever output is coming, it is according to the inputs given at that particular time of measurement. That's what the behavior of your combinational logic circuit. That means here there is no any past history is going to be considered in combinational logic circuit, you can see. I hope you are getting what I mean to say. For example, suppose something inputs for ABCD is coming like this. ABCD all are 1 and output is coming 1 for that inputs. And then next input is, let us say 0, 0, 0 something. Like this, suppose you are giving the next input. Then for that, suppose your output is going to be 0. Then here this output which is coming for the particular input combination is only depending on that input combination, not on the input combination coming prior to that input combination which you are preferring for. Are you getting what I'm saying here for this combinational logic circuit? Hello?
Yes, sir, clear.
Yes, sir.
Right? It means what was the input given before this? Right now you can see that before 0, 0, 0, 1, we have given 1, 1, 1, 1. So you are getting output for 0, 0, 0, 1, it is 0. So it is not like that you have given prior to this 0, 0, 1, 1, 1, that's why it is coming 0. No. If you, let us say here something 1, 0, 1, 0 input, and then after you are applying your 0, 0, 0, 1, then for each time when you are putting this combination, your output is going to be 0 only. That means your output is defined according to the combination of input, not on the what combination of input was coming prior to this or after this, right? So there is no any past history going to be kept in your circuit to give your actual and output at a given time. That is what the case of combinational logic circuit. But in sequential logic circuit, here there is a difference. That in sequential logic circuit, as per definition, you can see that the sequential logic circuits are the circuits whose output levels at any instant of time are dependent on the level present at that inputs as well as the feedback level present at the inputs. That means what is coming on the input side here, on this side, and at the same time it is also depending on the state of the circuit. State of the circuit means it is the feedback provided by the past history. That is what was the output before you given this input. That is also going to be considered in the sequential logic circuit. So that's why to keep record of what was the output prior to this input combination came, here there is a need of memory unit in the combinational logic circuit. So that's why in the sequential logic circuit, it is a combination of two things, combinational circuit as well as a memory element. It means you can see here that now this is combinedly known as the sequential circuit. In sequential circuits, your inputs are there as per the combinational logic circuit, as well as you are also giving one more input from here, that is you can see, and that is from the memory element. Now what this memory element will do, this memory element will store the output which was coming here. Okay, so that output also given as the input to this circuit, and that's why the combinational circuit will give you output based on two things. One, that is what coming here at the input side, it means what is the input combinations, as well as what was the last output came. So based on these two things, it's going to decide your output. And that is why in your sequential logic circuit, for the same input combination, your output can be different for the case of output coming from the feedback circuit, or you can say memory element. Are you getting? Hello?
Yes, sir.
Right?
Yes,
so
sir.
this is what the basic difference you have to understand first between the combinational circuit and sequential circuit. So combinational circuit has no memory unit requirement, but sequential circuit do require memory. Why that memory is required? Because to store the data coming at the output side for the next input combination. Okay, so that's why in the sequential circuit we need to have the memory element. So let's see the comparison between these two circuits now. If you have got just a basic brief about these two circuits. So very first point of comparison you can have is this one. That in sequential circuit, the output variables at any time or at any instant of time that is dependent on the present input variables and on the present state. Now understand the meaning of present state. Present state means the present state that was stored in the memory. Understand this thing, everyone. When I'm saying present state of the circuit means it is storing the last output came into the circuit. That is what data stored in the memory, right? Because that is applied as the input of the circuit at the time you are referring for getting output. So in the sequential circuit, these two things are going to be referred for giving the exact output. Whereas in case of combinational circuit, it depends only on the input variables coming at that time. It means your output variables at any instant of time is only dependent on the present input variables. There is no any present state. There is no any state of the circuit are going to be referred in case of combinational circuit. So that is the difference between these two circuits. Okay, so this is the first difference or comparison point you can have. Second point of comparison, we can have this one. And it is very easy to understand that in sequential circuit, we require to store the state of the art, or you can say the state of the circuits. That is what you can say past history of the output. So that requires a memory unit to store that output values. Whereas in case of combinational circuit, there is no need of any memory unit because there is no any state of the circuit or output of the circuit going to be stored. So that is a difference here, or you can say point of comparison. Then the third point of comparison can be like this. sequential circuit are going to be slower than the combinational circuit, whereas combinational circuits are going to be faster because the delay between the input and output is due to propagation delay of the gates only. Do you understand this, the difference? That the sequential circuits are going to be slower than the combinational circuit. Why is that so? Because here in sequential circuit, we require to take the data from memory unit also. And that's why the delay involved in reading the data from memory, that will be also added into the operation of the sequential circuits. And that's why your sequential circuits are going to be slower. Whereas in combinational circuit, there is no any data going to be read from the memory. Only the data coming from the input lines are going to be passed through the logic combination, that is the logic gate combination. So only propagation delay of that logic gates only going to be considered. But in sequential circuit, apart from this propagation delay of your logic gates, the time taken for reading the data from memory unit is also going to be considered, right? So overall time, if we are considering, then sequential circuit is going to be slower than combinational circuit. So that we can put a point of comparison here. Then the next point of comparison is this one, that the sequential circuits are comparatively harder to design. It means it is going to be more complex compared to combinational logic circuits. As in combinational logic circuits, there is no any connection between memory unit and output to input side. That means there is no any feedback circuits are there. So your combinational circuit implementations are going to be easier. Whereas in sequential logic circuit, we also need to get a feedback circuit through memory unit. So that circuit is going to be comparatively complex than what you have in combinational circuits only, right? So these are the points you have for the comparison. So are you able to understand these all comparative points? Or anyone have doubt to understand any one of this point?
Clear, sir.
Every one of you?
Yes, sir.
Okay. So see, before we start discussing about sequential circuits, you need to know about this difference and the comparison between your combinational circuits and sequential circuit. If we take example of these two circuits, you can give example as a more point of comparison here. Right? After this 4 point of comparison, you can add one more point of comparison also with the example. Like in, you can say in combinational circuit, you can put an example like adder, multiplexer, decoder, encoder. These all are the examples of combinational logic circuits. Whereas in case of sequential circuits, you can put the example of like serial adder. Then you can put the example of let's say counters, right? Shift registers. So these are the some very examples of sequential circuits. So that also you can put one more point of comparison after this all 4 by just putting the name of the circuits, which is you can giving example of this particular type of circuit. Now, if you remember the working of that half adder and full adder or any other encoder, decoder or multiplexer, in all that circuits you have seen that the output of that all circuits are only decided by your inputs. There is no any memory we have considered in that, right? There is only no any kind of circuit arrangement we have considered which can store the data, which can store the binary information. But now when we are going to start discussing about sequential circuits, in all that sequential circuits, you will be requiring the memory unit, or you can say the data storing element. Okay. Now, what is the data storing element? What is the smallest component, or you can say the part of circuit which is able to store the data? You can have basic knowledge about what is pen drive, what is memory card, right? Hard disk. These all things are what we have is a data storing device. They all are able to store the data in their capacity. For example, if you have a pen drive of let's say 2 GB, so your 2 GB pen drive is able to store the data of 2 gigabyte. 2 gigabyte means 2 into 10 raised to 6 byte. Now 1 byte is equal to how much bit? 1 byte is equal to Yes, anybody of you can say me this, what is the meaning of this? 1 byte. 1 byte is equal to how many number of bits?
8.
Yes, 1 byte is equal to 8 bits. So you can say that your 2 GB pen drive is able to store 2 into 8 into 10 raised to 6 number of bits. Right? 2 into 8, that means total 16 into 10 raised to 6 number of bits. So it is a large number of bits your pen drive can store. But when we are talking about a flip-flop and latch, that is the smallest unit, or you can say the smallest circuit component, which can only store a 1 bit of data. Understand this thing. That means if you are talking about your pen drive, which is capable to store 16 into 10 raised to 6 bit of data, that pen drive need to have 16 into 10 raised to 6 number of latch or flip-flop inside that circuit. So this is large number of circuit component required in that. So here we are going to start with discussing that smallest unit. That your sequential logic circuit will have a smallest memory unit, that is what able to store 1 bit of data. It can either store 0 or it can store 1. Only 1 bit, no any number of more bits. So that is what the smallest unit of memory, and that's what we starts with a latch. So what is a latch, or what is a flip-flop? So a flip-flop or a latch, which is commonly known as the bistable multivibrator circuit, which can have two stable states. Bistable means two stable states. That means it is a circuit component which will have output in two stable states. It can be either 0 or it can be 1 at any point of time based on your input applied. That's why this flip-flop or latch will be a device, or you can say a smallest component, which is going to store 1 bit of data by having any one stable state of its output by stable nature. It can remain in either of the state indefinitely. Indefinitely means for a longer period of time or infinite period of time. That means once you have stored 1 bit of data in the circuit at the output, let's say it is logic 1 or logic 0, that logic 1 or 0 at the output of this flip-flop or latch will remain for a longer period of time. And its states can be changed by applying the proper triggering signals. That means by applying proper input signal, we can start changing it. Means, for example, when you are saving some data in your pen drive, we are connecting that pen drive with our desktop or laptop, and then we are copying data from our desktop device to that pen drive space. So when you're copying the data, what it is actually doing, it is changing the state of that all flip-flops or all latches inside your pen drive, right? So how that is able to be done? For doing that, for making change of the data coming or data going to be stored at the output, we require to give the proper input triggering signal to all that latches or flip-flops. Okay, so what that triggering levels or signals we are applying, that is called the input of this flip-flop or latch. That we'll see later on. You will be able to understand at that time. Now, latch is used for certain flip-flop which are non-clocked. See, sometimes we are using the word latch, sometimes we are using word flip-flop. Ultimately, they both are doing the same task. Basically, latch is the initial component and flip-flop is the device or component which is developed by using latch to add the clock signal, or you can say enable signal. Once we will discuss both the component, you will come to know that what exactly the difference between these two is. And the flip-flops is going to be latch on to 1 or 0 immediately upon receiving the input pulse called set or reset. That means in the flip-flop or latch, based on the input given, either your output is going to be made to logic 1 or logic 0. When we are converting our output, let me just tell you here with the example. So so it will be easy for you to understand. Let us say we are talking about SR latch. Here there is no diagram. Let me draw the diagram. So what exactly you mean by that? SR latch means here, if I give you the block diagram of this SR latch, it is going to be like this. The symbol, or you can say block of the SR latch, can be like this. It will have two inputs. That two inputs, we can say it is S and R. Full form for S is set, R for reset, and there will be two outputs, that is Q and Q bar. So this is what you can say a symbol of SR latch, or you may call it is a flip-flop. Now, what is the working of this? In this latch, the output Q, there are two outputs Q and Q bar. So what data you are getting at this output Q is deciding what you are doing. That is what you are making to the change of output. That is whether you are setting the data output or resetting the output data. It means, for example, you are giving the input here S equal to 1 and R equal to 0. That is, we are giving the signal at the set. S stands for set, right? S for the set and R for the reset. So when you are giving the logic high value at the set input, your output Q is going to be set to 1. And when Q is 1, obviously Q bar is going to be 0. So this is, we can say, our latch is in set condition. Are you getting my point? So in the SR latch, when we are giving input 1 at input S, your output Q will be set to logic 1. That's why we call it as a set input. That whenever you are giving logic high at set terminal, your output of that latch is going to be set equal to logic 1. Similarly, when we are giving the logic 1 at the reset input by keeping S equal to 0, at that time what will happen? Your output Q will be made to 0, and your Q bar, obviously that is going to be logic 1 here, not 0 now, right? So what we can say here your output of this latch is made to be equal to 0. That means we call it as a reset condition. So that is what the purpose of set and reset name given to the inputs. That means whenever logic high is coming to the R input, that is the reset input, your output is going to be made to 0. And whenever logic high is coming to the set input, that is S, your output is going to be made to logic 1, that is, you can say, set, right? So this is what the set condition and reset condition of your latch. Now understand one more thing, that in SR latch, once you have set the output, that means once you have made your output Q equal to logic 1, then after, unless you make any change on the input side, your Q will remain to be set. What I mean to say by this? I want to say you that once you have made your Q equal to 1 by giving the value input at the S equal to 1, then after, if you are not giving any input here, suppose I am giving input 0 0 here, okay, then my output will remain 1 only. It will not change unless and until I give the change in the inputs with S and R. My output is not going to change, right? That means it will remain in the set condition or reset condition, whatever it is given prior to that. So that is what the purpose of this. So you can just now read out all these sentences, that will make you understand what I was talking. So the simplest type of flip-flop or latch is called the SR latch. It is called set reset latch. That is what we are talking here. And it will be having two outputs labeled as Q and Q dash or Q and Q bar, whatever it is, and two inputs labeled as S and R. The state of the latch corresponds to the level of Q. If your Q is logic high, we call this latch in set condition. If Q is equal to 0, or you can say low condition, we call that latch in the reset condition. Okay. It can be constructed using either two cross-coupled NAND gate or two cross-coupled NOR gate. How this kind of circuit can be developed, that we'll see later on. But right now you just came to know that how can we develop this kind of latch. It is just going to be developed by using two cross-coupled NAND gate or two cross-coupled NOR gate. That diagrams also I will discuss here. So using two NOR gates and active high SR latch can be constructed, and using two NAND gates an active low SR latch can be constructed. Now what do you understand by this? For if you are using cross-coupled NOR gate, inside this cross-coupled NOR gate means what? Suppose I just draw the diagram here, it will be easy for you to understand. Just a minute. I'm just going to draw the NOR gate here. So NOR gate will be like this. Okay, so this is one of the NOR gate, and I can have another NOR gate here. So there will be two inputs here. You can say here it is S and here it is R. Now another input of this NOR gate will be taken from the output of second, like this cross coupling. One of the NOR gate output will be given as the input of another NOR gate, like this. So when you do like this, here you will be getting your output Q, and here is your output Q bar. So this is what your internal circuit of your SR latch, right? So inside this box, this kind of circuit will be there. This is using two NOR gates we have discussed right now. So when you are using this two NOR gate cross-coupled circuit to develop your SR latch, it will give you active high SR latch. Now what do you mean by active high? Active high means your output Q will be set, means it is equal to 1 if you are putting S equal to 1 and R equal to 0. Right? And it will be making your Q equal to 0 if you are giving S equal to 0 and R equal to 1. That means the given input at either set input or reset input in the active high manner, that is logic 1, will be considered when it is making the change in the output side. That is called active high latch. But instead of this two NOR gate, if you have used the two NAND gates, let me draw that also here so it will be making you more clear. Now in the two cross coupled NAND gate, your circuit is going to be like this. This is the NAND gate I'm going to draw here. There also you will be having two inputs to each of that NOR gate, NAND gates. So these are the two outputs and these are the two inputs. Second input of the NAND gate will be taken from this cross coupling like this. Okay, so here is your input S and R, and here is your output Q and Q bar. So this is another way of implementing your SR latch. That is, your SR latch can be developed by using two cross-coupled NAND gates or two cross-coupled NOR gates. That is, you can see here with these two circuits. But when you are using two cross-coupled NOR gate, it will give you active high SR latch, and when you are using two NAND gates, it will give you active low SR latch. Now what do you mean by active low SR latch? Here in this NAND gate SR latch, what you have to do is, if you want to make your output Q equal to 1, you have to give S equal to 0 and R equal to 1. That is reverse thing. When you are giving S equal to 0, that is making output Q to be set. And when you are giving R equal to 0, it will make output Q to reset. So it is just the reverse thing, what it is going to happen in NOR gate circuit. Right? So this is what the difference between your SR latch that is implemented either using NOR gate cross coupling or NAND gate cross coupling. So is that part clear to everyone?
Sir, repeat once, please.
What part should I repeat here? Can you just give me exact points so I can elaborate on that?
So this active high and active low, difference between that.
Okay, let me just tell you. Active high means, just a minute, give me a minute. Active high means the signal which is going to activate your output ultimately. Just a minute, give me a time. I need to give you a. Okay, let me give you example here. Suppose I draw the signals. On the top, I'm going to draw the signal here first. Okay, so let us say this is what the signal I have. Something like this. Okay, this is the digital signal. In this digital signal, here you can see that is plus 5 volts, suppose. And here you can say 0 volt. Okay. So when there is a 5 volt, we call it as a logic 1. When 0 volt, we call it as logic 0. Then again 1, 0, like this. So if you are considering plus 5 volt as a logic 1 and 0 volt as a logic 0, it is called active high circuit. Okay. But instead of this, if you are referring to reverse, that means when there is a logic 1, you consider it as a, means when there is a plus 5 volt, you consider it as a 0. And when there is a 0 volt, you consider it as a logic 1, like this. Then it is called active low circuit. Am I making this thing clear to everyone now?
Yes, sir.
Okay. So the active low and active high means how you are getting your logic implemented. What value of voltage you are considering for your logic 1 and logic 0. So that is what it is going to make your circuit, whether it is active low kind of circuit or active high kind of circuit. Okay, so this is about the basic thing of your SR latch. Let's move ahead to discuss it in further detail. So here first let us start with NOR gate SR latch. Here is the symbol. There will be 2 inputs, 2 outputs. That is what just we have discussed, right? And this is what you can say a logical symbol, or you may call it as a block diagram of this SR latch. Now this is the diagram with using 2 NOR gate cross coupled with each other like this. You can have the circuit like this. There is 2 input R and S. There is 2 outputs Q and Q dash. Now how this circuit is going to work? Here is the truth table you can have. Now in this truth table, you can see first column is for the given input at the set terminal, that is S input. Second column is for the R input, or you can say the reset signal. Then Qn, Qn plus 1, and last one is the state. So here what is Qn? Qn means it is the present state, and Qn plus 1 is your next state. Okay. Suppose you are giving some input at R and S 0, 0, for example, like this. Let us discuss as per the coming points here. Let us say we given S equal to 1, R equal to 0. Okay. So when you are giving S equal to 1 and R equal to 0, what will be your output? Let us say present output is 0. That means your output Q is 0 right now. Okay. Before you have applied R equal to 0 and S equal to 1, let us say Q was 0. So what will happen next to this input given? That is what your 0 Q will come at the input here for the NOR gate. Let me just write down the NOR gate numbers here so it will be easy for you to. Let us say I'm giving the NOR gate number 1 here and NOR gate number 2 here. So you can see that prior to the application of R and S, right, let us say we understand that output Q is equal to 0. Before you have applied S equal to 1 and R equal to 0, your Q was already 0. Okay. Now we are calculating what will be your next output because of your R and S input given. So you can see that the Q which was 0 will come at the input of NOR gate number 2, and another input is coming from S. So the two inputs of NOR gate will be 1 and 0. So that will give you output of this NOR gate number 2 to be 0, because you know that the NOR gate will give you output only logic 1 when both the inputs are 0, right? So what this will do, this Q dash will go to the second input, that is, you can say NOR gate number 1. So now you get both inputs to the NOR gate number 1 to be 0, and so the output Q will change from 0 to 1. Understand this thing? Before you have applied S equal to 1 and R equal to 0, your output was Q0, and that's why it has changed from 0 to 1. That is what we call it as a set condition. So you can see that the next output becomes 1, and this change of the state we can call it as a set. Another case here, we are saying that if you are giving S equal to 1 and R equal to 0, but before that your Qn is only 1, then what will be the next output? It will be only 1, means it will not change it. It will remain as it is. So then we can say it is a set condition. Have you understood this? When we are giving S equal to 1 and R equal to 0, your output Q will be kept 1 if it is already 1. And if it is 0, then it will be converted to 1. Ultimately, whenever there is S equal to 1 and R equal to 0, your output Q will be made to be equal to 1. That is what we call it as a set condition. And whenever Q is equal to 1, Q dash is always going to be 0. So this is the first condition you can understand. That is what we call it as a set condition of the latch. Is that clear to everyone?
Yes, sir.
Okay. So now the next state we consider, let us say S equal to 0 and R equal to 1. So if S equal to 0 and R equal to 1, that means here, if I just show you in that circuit, here now I'm giving S equal to 0 and I'm giving R equal to 1. Okay. Before that, let us say my Q is equal to 1 and Q dash was 0. That's why. So what will happen here now? So you can see that you have given R equal to 1. Okay. This Q dash 0 was coming here. So what it will do, it will convert this output Q from 1 to 0, and that 0 will come here at the input of the second. So this both 0 will make your output to be 1, right? So that is how you can see, for the case if your output Q was 0, it will kept 0 as it is, or if it is 1, then it will be converted to 0, right? Before, if it is like, see, if you understand this, before we have applied R equal to 1 and S equal to 0, let us say, if I remove this part first, okay, suppose before we have applied this, let us say your Q was already 0, okay, and Q dash was 1. This is the earlier condition. So then for this case, what will happen? This 1 will come here, so 1 1 will give you output 0, so 0 will remain as it is 0, and that 0 will come here, so you will be getting 0 0, so output remain 1 only. That means there is no change in it. So if earlier your output is 0, then it will be kept 0 only, but if it is 1, then it will be converted to 0. So whenever you are setting R equal to 1 and S equal to 0, your flip-flop or latch output is going to be 0, and that is what we call it as a reset condition. So are you able to understand this reset condition? Hello? Is that clear to everyone?
Yes, sir.
Okay. So this is what we have discussed about set and reset condition. Now next, we can say when s equal to 0 and r equal to 0, both are 0 0, and if your q is equal to 0, what will be output? It will remain 0 only. And if you are setting r and s both 0 0, and if your qn is equal to 1, then what the next state is going to be? 1. It means no change. So that is what we can say, it's a no change state. How it is going to be done? If you want to understand that, let me just explain one by one. So here, let us say my initial output is 0 1 here. Okay, and now I'm giving r and s both 0 0. So when I'm giving r and s both 0 0, what will happen? So so this output q will come here. So this 0 0 will give me output 1, and this 1 will come here. So 0 1 input to this will give me output 0. That means there is no change in this. Okay, and if my earlier output was 1 and 0 like this, so what will happen here? In that case, you can see that this 0 will go here. So 0 0 will make your output 1, and that 1 will come here. So 1 0 will make your output to be 0. So there will be no change. So whenever your r and s both are set to be equal to 0, your output which was there earlier will remain same. There is no change, and that's why it is called no change state of the latch. So there is three condition at the output of this latch. Either it can be set by giving s equal to 1, or it can be reset by giving r equal to 1, and it can be kept same data by making r and s both equal to 0. Right? So this is like you can have understood about your writing the data from pen drive. Suppose you are storing some data to your pen drive. So at that time, you are making change to the data stored in that. So you are giving either set or reset input. But when you are taking out your pen drive, means it is not connected anywhere. At that time, you can say your R and S both are going to be 0 0. So there will be no change in the data output. So it will be stored. Whatever data that is given, it will be kept as it is. Okay. So these are the three conditions of the latch at the output side of this SR latch, and that is going to be considered as a valid input combination and valid output state. But now for the last combination, that is when S and R both is equal to 1 1. In that case, what will happen? If your Qn is equal to 0, your Qn plus 1 cannot be predicted. It can be 0 also, it can be 1 also. That's why it's put a cross mark over there, considering don't care. And when both are 1 1 and your Qn is equal to 1, then also your output Qn plus 1 cannot be decided. It will not be fixed. Right? It can be 1 also, it can be 0 also. That is why this is called indeterminate or invalid state of the latch. So this last condition we should always avoid, that your SR latch should not be given your both the input S and R simultaneously 1. Okay. So that is what you can say a invalid condition, and it is not allowed in the case of SR latch. So are you able to understand this NOR get SR latch? That is what a kind of nature active high. That is when you are putting S equal to 1, it is going to set. When R equal to 1, it is going to reset. And when both of them are 0, it is no change. And when both are 1 1, it is called invalid case. Have you understood this?
Yes,
Okay.
sir.
What about others? All are you getting
Yes,
this?
sir.
Okay. Okay, that's fine. So now let's move to the discussing next type of SR latch. Next type in the sense developed using NAND gates. Okay, so let's see that one now. So now in NAND gate SR latch, you will be having the cross coupled NAND gates like this. And if you look at the truth table here, you can see that when S equal to 1, R equal to 0. If your Qn is equal to 0, your Qn plus 1, that is going to be, you just look at here, it is going to be 0, right? That's what we have seen here. Look at here in the diagram also, right? When S equal to 1 and R equal to 0, if your Q is equal to 0, then what happens here at the output side? Your Q dash is going to be 1, and that will make your Q to be remain 0, right? So there is no change, you can see like that. Then after, when you keep S equal to 1 and R equal to 0, it's, if your Qn is equal to 1, then what happens? It will make it to 0, and that is called reset condition. Understand this thing. In the previous case of NOR gate latch, if you remember, when S equal to 1 and R equal to 0, your latch is going to be set. It means the value provided logic high at the particular input is considered. That means if you are putting logic high at S, it is going to set. And if you are putting logic high at R, it is called reset. But in this case, when you are using a NAND gate SR latch, it's doing reverse. When you are putting logic low, it is acting the circuit. That means right now you can see in this combination, when we have kept R equal to 0, for the case when R equal to 0, it's going to reset, not when R equal to 1. If you just look at back here in the previous circuit, by just taking you back here, you just see here in the case of NOR gate. In NOR gate, when R equal to 0 and S equal to 1, that is going to set the circuit, means your output is going to be made 1, and that is what we call it as a set condition. But compared to this, in case of NAND logic, it is reverse. That is when your S equal to 1 and R equal to 0, your output Qn plus 1 will made to be 0. It means it is called active low kind of SR latch. That is when 0 is applied, it is acting the circuit, right? Likewise, when you are putting S equal to 0 and R equal to 1, if your Qn is equal to 0 earlier, it will convert it to 1. And if it is Qn equal to 1, it will keep it as 1. And that is what we call it as a set condition. In short, you can simply understand between NOR logic gate circuit and NAND logic gate circuit here, that your latch will be set when S equal to 1 in case of NOR gate, but when S equal to 0, it is going to set when it is NAND gate. Okay, and similar to that here, when both are 0 0, it is active signals, and that's why it is giving you invalid state. In previous case, when they both are 0 0, it was considered to be non-change or no change state, right? But that no change state here will come when both are 1 1. So that is totally reverse here, and so that's why it is called a no change state, because at that time there will be no change in the output state of the latch. So now can you differentiate between the working of these two latch when it is implemented using NOR gate and when it is implemented using NAND gate? Hello? Hello everyone. Can you understand what I'm saying here? Can you just unmute yourself and give me reply so that I can hear you? Because I'm not always going to look at the chat, what you are writing there. Isan, can you hear me?
Yes, sir.
Okay. Parita is saying the yes. Isan, can you hear me? Vrunda, are you there?
Yes, sir.
So are you able to understand this, what I'm talking about, this two type of latch, active low and active high using NAND and NOR logic
Yes, sir.
circuit? Okay.
Yes, sir.
Okay, that's fine. So now, once you have understood the latch using NOR gate and NAND gate, now you are able to understand the working of flip-flop. So flip-flop will be taking latch as a block inside, and there will be outside one more circuit will be added to add the enable signal. So that is only going to put a difference between them. So now let us see the SR flip-flop. That is called gate SR latch. See, in earlier two circuits we have discussed, there is no any other enable signals. There is only two inputs, one that is to set the output, one that is to reset the output. There is no any other input was given. But now when we are talking about flip-flop, there will be third input which is known as the enable signal. You can look at here in this symbol. Third input given here, that is EN. Here this third input is called enable input. S and R will be as it is. It was there in the SR latch earlier we have discussed, right? And output Q and Q dash, that is also there. But new thing here in SR flip-flop, that is the enable signal. It means this flip-flop will work in the same manner as your SR latch was working. But the difference here is it will be either going to be set or reset based on the input given at S and R only when this circuit is going to be enabled. Means that enable signal is put a logic high, right? That is only the difference here. You look at here the circuit, internal circuit. So you look at here the internal circuit using the NAND gate. So the NAND gate logic circuit is here. See, this much part was there already. This was the part for the NAND gate SR latch. Apart from there, we have added these two NAND gate extra. So NAND gate number 1 and 2 extra we have added here. That is to apply with this third input signal, that is enable. Now here what will happen here? You need to know that suppose I want to get my output to be set. I give S equal to 1, R equal to 0, for example. So that input which is given to S, and let us me write down here something S dash and something here, let us say R dash. So that S dash and R dash, which is output of your NAND gate number 1 and 2, which will be applied to the input of your latch, right? This is your latch. Right now, this is the part which I just encircled is your latch. That is what we have discussed previously. So output of this NAND gate number 1 and 2 will be applied to the latch circuit. So here when this output S dash and R dash will be given, suppose you given this enable signal to be equal to logic 1. When enable signal is equal to logic 1, you can see that one of the inputs of this two NAND gate number 1 and 2 will be logic 1, right? Now, what is the output or what is the working of NAND gate? You know that the truth table of NAND gate is that whenever there is both inputs are logic 1, your output is given to be 0, right? And whenever there is another combination, either 1 0 or 0 1 or 0 0, your output is going to be given as a 1. So what happens here? You can see that whenever your enable signal is given to 1, your both the output set is equal to 0 1. So you can give you can see that this is a NAND gate latch. So NAND gate latch is an active low kind of latch. So active low is getting 0 at S dash. So your output is going to be set and Q dash is going to be 0 like this. But instead of this, suppose your enable signal is not 1, it is 0. If your enable signal is 0, this input to the NAND gate 1 is 0 and this input to the NAND gate number 2 is 0. So what this will do? This will give you output of both the NAND gate to be logic 1. Here also you will get logic 1 and here also you will be getting logic 1. That means your S dash and R dash, which is given to this low acting latch to be 1 1, and that is going to give you what? There will be no change. It will be putting no change at the output side. So in this flip-flop, when we are adding this enable signal, your input provided here at S and R will only be applied to your latch if there is a enable signal is logic high. If enable signal is not logic high, your output will not be able to change. Means your latch will not getting the signals for making set or reset condition to your flip flop. So can you understand this? What I'm talking about, the difference between latch and flip flop?
Sir, can you explain no change condition again?
Okay. See, what I'm saying here is when there is the addition of this enable signal, prior to this enable signal was added, what was the case? If enable signal was not there, you are not having these two NAND gates, right? Let us just talk about the latch first. Let me remove all this thing. So latch means only the part that is coming afterwards. Okay. So what I'm saying is, suppose this is what your latch. This much part is your latch. Right now you forget about the NAND gate number 1 and 2. Okay. You directly consider that you are giving your R input here and you are giving your S input here. So that is what your NAND gate latch. Now in NAND gate latch, if you remember the truth table we have discussed, that when your S equal to 1 and R equal to 1, when both the signals are 1 1, you will be getting here output to be no change, right? Means if it is 1 0, it will remain 1 0 only, and if it is 0 1, it will remain 0 1 only. So whatever output is there, it will remain as it is. So that's what we can say it's a no change. It means in the NAND gate latch, when you want to get no change at the output side, your S and R input applied here, they both should be logic 1. Okay. Now that condition will always arrive when your enable signal is kept 0. If I keep enable signal to be 0 here, if enable signal is coming 0 here, now whatever value of your S and R is, whether you put S equal to 0, R equal to 1, or S equal to 1, R equal to 0, or they both 0, or they both 1, whatever value of you keep for S and R, your output of this NAND gates number 1 and 2 is going to be 1 1, isn't it? Because you can see that this NAND gate can only give you output logic 0 if they both are 1. But as here there is 1 0 already coming, so they both never going to be 1, right? And that's why your output is always going to be 1. Same way here also 1 0 is coming here. So whatever value of R here, it's not going to be considered. Your output going to be logic 1 here. So when there is enable signal is 0, your circuit is disabled, like that you can say, right? So disabled
Yes,
means
sir.
your output will not be changing. So whenever you want to make anything change in the output side, you have to enable your circuit by giving logic high at the enable signal. So whenever you give logic 1 to this enable signal, then only the value coming to R input and the value coming to S input will be passed on to this S and R of the latch. And that is how your latch is going to be either set, reset, or no change. So that action is only able to applied if your enable signal is provided. Is that clear now?
Yes, sir.
Okay. What about others? All are you getting this?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay, that's fine. Now let's move ahead. So here you look at the truth table. This is the truth table for the enabled SR flip-flop now. It is just the thing we have discussed. So you just get it known here now. So let me just take it step by step. Before with that, remove all this notation. Okay. So now you look at here, when the input enable signal is provided 1, if your S equal to 1 and R equal to 0, your output coming to this NAND gate number 1 and 2 will be 0 and 1. right? So what this will do, this is going to make your output to be set, right? Means your qn plus 1 is going to be 1. Okay. Then after, if it is earlier it was 1, then it will kept as 1, so it will be giving you set condition. And if you are connecting enable signal equal to 1 and putting s equal to 0, r equal to 1, then your output is going to be resetted. So that's what you can say reset condition. When enable signal is 1 and you put your SR equal to 0, 0, you will be getting your output to be no change. And if your enable signal is 1, if you give your S and R equal to 1, 1, then it is giving you invalid case here. That's what we have considered earlier. But now this was the case, means your SR latch will work in the same manner if you provided enable signal equal to 1. But if you provide enable signal equal to 0, then after whatever your S and R value will be excess, your output will not be going to be changed, means it is remaining same, so that is going to also give you no change. So here two no change state will come. Once when your enable signal is 0 and other when your S and R both are 0. So that is what the flip-flop is. This enable signal is not there in the SR latch. It is there only in flip-flop. Okay, so this is only the small change you can consider between latch and flip-flop. Is that clear, everyone, now?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now, next flip-flop we want to discuss, that is D flip-flop. So this D flip-flop is going to be made by using SR flip-flop, right? But here two separate signals are not going to be given, because you have seen that in earlier case that when you make S and R both equal to 1, 1, that is considered to be an invalid state at the output side. It means in the SR flip-flop, we have to make sure in our circuit design that the input coming to the S and R will never going to be same at the simultaneous time, right? So that is going to be overcome here in the D flip-flop, that here only one input will be given, that is the D input. It is called data input, and one more input, that is the enable signal. Output will be as it is, Q and Q dash. If you look at the internal circuit, it is same as what we have just discussed before, that is SR flip-flop, right? Only the thing change here is instead of giving two separate input R and S, we are giving only one input, and second input is generated by using NOT gate. That means if you are providing 1 over here, 0 will go to the next input, like that. So they're never going to be simultaneously same. And that's why your invalid state of output circuit or output data will never come. That is only the purpose here. So that is what the thing here. Now you can understand the table, that when your enable signal is 1, if your data input is 0, what will happen? The 0 and 1 will come to the NAND gate. Let me give the number of NAND gate here. So here I can say, I can give NAND gate number 1 here, NAND gate number 2 here. So you can see that the input of NAND gate number 1 is 0, 1, and input to the NAND gate number 2 is 1, 1. So what will happen to the latch? Your latch will get 1, 0 here. So it is going to, if your Qn is equal to 0, it will make your output to be equal to 1. Kept equal to 0. So there is no change, you can see. So when the data input is 0, and if your Qn is equal to 1, then it will be giving you output Qn plus 1 is equal to 0. So that is what it is going to be give you reset condition. It means when data input is 0, it will give you output state of the latch to be 0. That means it will reset it. Second state is when enable signal is 1 and you put your data input to be equal to 1, then it is going to give you output equal to 1 in all the conditions, right? Whether if it is 0 prior to that or 1, it will keep it output to be equal to 1. So it is called set condition. And the third case, when enable signal is 0 At that time, whatever data input is given, your output will not have any change, so no change state will be there. So here in this D flip-flop, we can overcome that invalid state case. Here there is no chance that you will be getting output of this flip-flop to be invalid, because there is no simultaneous inputs are coming same, that is going to be active high. So can you understand this working of D flip-flop? Hello? Hello? Is that clear to
Yes,
everyone?
sir.
Yes. Yes, sir.
Yes, sir.
Yes, sir.
Yeah. Is there any delay in communication? The voice coming later on there, or is it okay?
It's okay, sir.
Okay. I'm just asking because I'm getting a response a little bit later on, means with some delay. That's why. Anyway, let's come to the point of flip-flop. See, this is the second type of flip-flop we have discussed. First flip-flop we have discussed, that is of RS flip-flop. Then second, right now we are just talking, that is a D flip-flop. Okay. The advantage of this D flip-flop is we can overcome invalid state of the output of the flip-flop. Now next is JK flip-flop. So what is JK flip-flop? In JK flip-flop, this is the symbol. Here input signal names are changed from RS to JK, right? It is not now reset and set input, it is J and K input. Enable signal is still there. Outputs are also already there, same as it is, Q and Q dash. Now internal circuit, you can look at here. So the internal circuit of this JK flip-flop is like this. Here also there is a separate NAND gate number 1 and 2 are used with the 3 input terminals. And this is your SR latch, right? SR latch is still used here. So this is a latch, and apart from latch, there is the 2 extra NAND gates are connected. But these NAND gates are having 3 inputs. The third input is taken from the output of the latch. You can see here, from the output of latch, it is connected to here, as well as from other output, it is connected here. So that is the thing you have to understand. Otherwise, enable signal and JK inputs are there. Now look at the truth table. Here the thing which was done by set and reset input is going to be done here by J and K input when there is a enable signal is given. It means whenever enable signal is equal to 1, and if you make your J equal to 1, okay, and K equal to 0, and if your Qn is equal to 0, so what will happen? The input to this signal or NAND gate number 2 is 0 0 at the 2 inputs, and that's what giving you output equal to 1, right? And at the same time, output of the NAND gate number 1 will be equal to 0, because your J is 1 there, K is 1, and feedback coming, that is also 1. So this 0 1 given here will make your output to set, so Q will become 1, and that is what you are getting here. Now next is, if your enable signal is given 1 and JK is 1 0, and if your Qn is already 1, then what will happen? It will keep that 1 as it is, means your outputs will be of the NAND gate number 1 will be 0 and 2 will be 1. So your latch will be set only, so it will be called as set condition. Same way, another case, reset condition, when enable signal is given and J is 0, K is 1, so it will make your circuit to be reset. Then no change state when J and K both are 0 0, and one more state here added, that is called toggle. So what is the meaning of this toggle state? Toggle state is that if your output given 0, then it will be converted to 1, and if it is 1, it will be converting to 0. So what it is this toggle state will come. Let me just tell you about that. See, when enable signal is set to be equal to 1, and if you are keeping j equal to 1 as well as k equal to 1, in that case, if your output here is 0 and 1, then when you apply this signal, your 0 will be converted to 1 and this 1 will be converted to 0. And if it is already 1 0, then this 1 will be converted to 0 and 0 will be converted to 1. So whenever there is a equal condition at j and k, means they both are given equal to 1, then your output will not have invalid case, right? In the previous cases, that is RS flip-flop, when you are giving j and k, or sorry, r and s both equal to 1 1, that was a invalid state, or it was giving the output state to be invalid. But here it is not that case. Here when you are giving j and k both equal to 1 1, your output of the latch is going to be toggle. Toggle means converting either from 1 to 0 or 0 to 1. It means whatever state was there, it will be giving the opposite state there. That's why it is called toggling state or toggle state of the latch. So here also there is no issue of invalid state at the output side. That is what the more advantage here you are getting. And here you are having also the option of giving j and k separate. That is what not there in the case of D flip-flop. In D flip-flop, you are able to give only one input, that is the data input. Right? So here that is the advantage. And when there is a enable signal is 0 0, whatever value of j and k you are giving, there will not be change any output. So it is called no change state. So are you able to understand this JK flip-flop?
Yes, sir.
All of you are getting this or not? I'm only getting yes from one student only, right? What about others? Isan is writing there, yes, sir. Okay, I'm getting yes from many of you now. So this is the discussion of 3 flip-flop we have done, starting with RS flip-flop, then D flip-flop, and now JK flip-flop. So these are the 3 different types of flip-flop. Ultimately, you can see in each of these 3 flip-flop, we have a RS latch inside. Only the thing getting changed is the input side. There is a various combination of NAND gates we are taking here to get the change in the operation. Okay, and that accordingly we are giving the new name to the flip-flop. Okay, ultimately that is a latch only, getting either output Q to be set or reset condition or no change condition. Now the next type of flip-flop is T flip-flop, and it is a toggle flip-flop. Now this toggle flip-flop is actually not a new flip-flop. It is same as that what we have in case of JK flip-flop. Only the thing getting changed here is we are combining the input J and K to give a single input, that is T. T means toggle input. So what here it will be like this. You can see this. It is very same as what we have seen in the previous case. But here the only thing we have done is we have combined the 2 input terminals J and K together to give a single input T. That is what we call it as a toggle input. So this will work like a JK flip-flop only. But here, as we have combined the 2 inputs, we are only providing one inputs. The case will be reduced. Means whenever enable signals are given and toggle input is 0, then there is no change, because when toggle input is 0, your J and K both will be 0 0. Right? If I just separate out this toggle input, you can say that here is the J input and here is the K input, right? So when you can say your toggle input is 0, your J and K both will be 0 0. So it will give you no change. And when toggle input is 1, your J and K both will be 1 1. So it will give you output state to be toggle. Right? That is only the case here. No other case will be there. Means this toggle flip-flop is not going to be used for your output getting set or reset, because it is either going to be toggle or there will be no change, because when enable signal is 0, you will be again getting no change. So this toggle flip-flop is not having any set or reset state at the output side. It is either going to keep no change at the output side or toggle state at the output side, because this is just the revision in the JK flip-flop just by combining two input terminals. Am I making this thing clear to everyone? Hello? Hello?
Yes, sir.
Is that okay to everyone?
Yes, sir.
So these are the all different types of flip-flops, and these all flip-flops can be considered as a smallest unit of memory. In the starting of our today's session, I told you that in sequential logic circuit, we required to have a memory unit, and that memory unit will do what? It will store the output data in that memory part. That means here you can see this, any of this flip-flop, R, S or JK or D or T flip-flop, you can use to store your data of the output of your circuit, of your combinational circuit, and that data can be applied at the input of your combinational circuit to complete a closed loop and to make a feedback path, and so to develop a sequential circuit, right? So this flip-flop will be the main memory block which is enabling us to have a sequential logic circuit. Your each flip-flop, whether it is RS flip-flop, D flip-flop, T flip-flop or JK flip-flop, they all can store 1 bit of data. 1 bit of data means where that 1 bit is going to be stored, that 1 bit is going to be stored at the output Q of the flip-flop, right? So if your Q is equal to 1, you can say that that data stored at the flip-flop will be logic 1, and you can say your flip-flop has been set. And if the data stored at the flip-flop output equal to 0, you can say that your flip-flop has been resetted. So according to that, now suppose you want to store the data. Let us say I have the 4-bit binary data. Suppose I have 0101. So if you want to store the 4-bit data, you require to have 4 flip-flops, right? And you can connect them in that manner, and you can set the value of 2 flip-flop to be equal to 0 and 2 flip-flop to be equal to 1. So in that way, you can get your data 0101 to be stored in that flip-flops. So are you getting about the concept of memory unit and this flip-flop? Hello, everyone. Are you getting this?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so this is what the introductory part of this chapter, that is the sequential logic circuit, that you have to learn first about this various flip-flops, and that is what we have completed now. Now we can move inside this chapter to discuss about various other circuits and other sequential logic circuits, starting with the registers. But I think that we should keep for the next session, right? So today we are keeping up to this only. If you have any query in the point and topic we have discussed in today's session, that is all these different types of flip-flops, introduction to that combinational circuit, sequential circuit, and the comparison. If you are having any kind of doubt, just let me know here. We may give you 2-3 minutes for that. If you are having any doubt, we will be solving here. Otherwise, by taking your attendance, we'll be ending your session. So everyone, please just take a quick recap of the thing we discussed today about this all 4 different types of flip-flops, and you just raise your questions, whatever you have. We'll be discussing that questions in 2-3 minutes, and then we'll be ending the session. Okay, meanwhile you raise your question, you can also start giving your attendance. Yes, is there any question? Yes, Parita is asking something. Yes, Parita, is there any question with you?
No, sir.
Okay, I seen that your raise your hand is here.
Sir, can we compare all the flip-flop and their advantage over each other?
Yeah, of course, why not? You can compare them just as I told you. Starting with RS flip flop, that is what you can say the basic kind of thing, because in that RS flip flop, we are having the same principle of that RS latch only. Only the adding thing is that your enable signal. It means if enable signal is given, your RS flip flop will work like a RS latch. If enable signal is not given, then RS flip flop will not going to give you output change. It will remain same. But in D flip flop, you are having advantage of that invalid state, means you are not getting any kind of invalid state in that, because you are combining both the inputs R and S together to give your single input, that is data input, so that state of output invalid zone can be removed. So it will be giving you advantage, means it will remove some restriction in your circuit design. So that will be advantage in case of D flip flop. And if you just comparing D with RS, you can get this point of comparison, right? Then from D flip flop we came to the JK flip flop. So in JK flip flop, we are giving J and K separate input. Then also you are not having the change in the you are not having the invalid zone at the output side, because in that case even you make your J and K both one simultaneously, your output is going to get another state of change, that is what we call it as a toggle state. So that can be used whenever you require to toggle your output. So that is putting an advantage there, that you means it will be giving you feature of toggling at the output side, right? And one more thing, that in the T flip flop what you can give is that there as you are combining your J and K together, that kind of flip flop can be applied wherever it is only required to get a toggle state. Sometime in the circuit, in the sequential circuit development, you need to have such kind of feature that you do not need to have set or reset condition. You only want to toggle the state whenever something get changed in the input side. So in that kind of application, you can just go with the toggle flip flop, right? So these all flip flops are having advantage and disadvantage based on their application. So that is not going to be like this is the best one and this is not a good one, so we are only going to choose the best one always. No, it's not like that, right? So they all are having advantage and disadvantage based on their application. So depending on the application, you need to choose proper one. Is that clear?
Yes, sir.
Okay, so I think that's all from my side today. We can discuss the remaining parts also, but I think that will be not giving you the advantage for learning, because it will be getting more stuff to remember today itself. So we'll be taking remaining part of this chapters in our next coming lectures. Okay. So I hope that you all have given your attendance. And if you have any other question, please ask me here, or otherwise we can stop the session. Okay, I think now there is no one is there remaining to give attendance. All of you have given it. So now I'm going to end the session. Okay, thank you all. We'll meet again in our next session. Thank you. Have a nice day.
Thank you, sir.
Thank you.